Dear learners, welcome to the massive open online course on algebra. Today's module, polar representation of complex numbers. In this module, we are going to learn about what is meant by complex numbers, the polar coordinates in the plane, and the polar representation of complex numbers. Numerous examples associated with these concepts are also illustrated. Over the past centuries, the numerical system evolved from whole numbers to integers, which then led to the identification of rational numbers. Numbers which could not be expressed as rational were observed and termed as irrational numbers, and both of these combined were termed as real numbers. During the first century, mathematicians came across various equations like x squared is equal to minus a, which did not have a solution in the real number system. For example, if you consider the number system x squared is equal to 25, in this equation, x squared, when you take the square root of this number, the square root of 25 is 5, or plus or minus 5 to be exact. If you consider the equation x is equal to plus or minus root of minus 25, what is the solution of x? The answer to this does not exist in the real number system. Hence, the roots of this equation had to be determined in a different number system. Hence, the birth of the complex number. The roots of this equation are of the form x is equal to plus or minus root of minus a. This leads to the introduction of the concept of imaginary numbers or complex numbers. We denote root of minus 1 with the symbol I, which denotes iota. Complex numbers are used in many varieties of fields in real life. They are widely used in electronics, electromagnetism, and certain fields of engineering. For instance, in electronics, complex representation of a circuit having both current and voltage, where V is a real axis part and I is the imaginary axis part, are put together as a single complex number. Introduction of complex numbers. A complex number is the sum of a real number and an imaginary number. A complex number is of the form a plus ib and is usually represented by z. Here both a and b are real numbers. The value a is called the real part, which is denoted by real part of z, and b is called the imaginary part, namely imaginary part of z. Also, ib is called an imaginary number. The complex numbers can also be defined as ordered pair of real numbers. C is equal to the set of all ordered pairs a comma b such that a comma b belongs to R. That is a representation of the complex number system, and addition in this system can be defined as a comma b plus c comma d is equal to a plus c comma b plus d, and multiplication is defined as a comma b c comma d, which is equal to ac minus bd comma bc plus ad. Commonly, the ordered pair a comma b is denoted as a plus ib, so that I is 0 comma 1, the ordered pair 0 comma 1, and we notice that I squared is equal to minus 1. In fact, this is the definition of complex field. The complex numbers are visualized as a complex plane, where the complex number a plus ib belongs to C is associated with the ordered pair a comma b belonging to R squared. During the early decades of the 19th century, the complex numbers became an accepted part of mathematics, in large part due to the development of complex function theory by Augustin Cauchy. So, as we can see, the complex number representation is what we are going to discuss in this section. So, C is equal to the ordered pair a comma b such that a comma b belongs to the set of real numbers. Now, we have to keep in mind that complex numbers are not unidimensional. They are two-dimensional in the sense that everything is represented as an ordered pair, as we already have seen. So, this a comma b such that a comma b belongs to R is a Cartesian representation, in the sense that a and b are with respect to an x and y axis. Now, this is also represented as a plus ib such that a comma b belongs to R, both of which are representations of the complex plane. The addition here is defined in this manner, a comma b and c comma d. So, a plus c. So, the common terms, the first terms are added together and the second terms are added together. Next, multiplication is also done in such a way that AC minus BD. So, A the first two terms minus BD and then BC the mean terms and the extreme terms, BC plus AD. So, these two are the multiplication of addition and multiplication of two complex numbers have been discussed. Now, we have one more representation of the complex number, and that is the polar coordinate. Polar coordinate or polar representation of the complex number. So, as I said earlier, you have Cartesian representation, next we have polar representation. The polar representation is quite easy. So, I have an x axis and a y axis. If this were the Cartesian method, you would represent m of x comma y with respect to x axis, it is this far, and with respect to y axis, it is this far. So, from x it is here and from y it is this far. But in polar coordinate, we discuss it in an entirely different manner. Here we are talking about angles. So, angle with respect to the horizontal axis. So, this means that when I represent a complex number, you need to think of it as an arc moving along a spherical structure. So, this is a unit circle, and in the unit circle you can see that this particular line, now here it has stopped here, but whereas it is actually moving from 0 to 2 pi or 360 degree, which is why the angle T is represented as 0 comma 2 pi, and R being the length of this arc. This arc is represented by R, the length of this arc is represented by R. So, when I convert a Cartesian coordinate to a polar coordinate, what I am doing is R is equal to root of x squared plus y squared, and T being the angle which can change from 0 to 2 pi. So, R comma T is a polar coordinate of any term. So, if M is a representation in terms of x and y, if I give you a number x comma y from the complex plane, in that case I can represent it in terms of a polar coordinate as R comma T, where R represents the length of this arc and T represents the angle that this arc is making with respect to the x axis. So, the position is, if I say where is mx comma y, it is actually, it is at an angle T from the x axis and at a length say R from the origin. That is the correct interpretation of a polar coordinate. Next, we shall see some further details with regard to the polar coordinates. So, x is represented as r cos t, t being the angle and r being the vector r. So, r cos t and y is r sin t. So, y by x is the slope. So, r sin t by r cos t is tan t, and t is equal to tan inverse of y by x plus k pi. So, this is the usual representation of a polar coordinate, especially with regard to the angle. Now, we know that the angles can change with regard to the position of x and y. Hence, if x is non-zero, if you have x is non-zero, then k can be 0, 1 or 2 depending as in how x is represented. So, x can be, if x is greater than 0 and y is greater than or equal to 0, then you have k to be 0. Whereas, if x is less than 0 and for any y, k is 1, and when x is greater than 0 and y is less than 0, you have 2. So, which means that what will be the value for k here is depending on how x and y behave, you can change the position, the values of k to be 0, 1 or 2 here. So, whereas what if x is 0 and y is non-zero, then t can only be 2 values, namely pi by 2 for y greater than 0 and 3 pi by 2 for x greater than 0 and y less than 0. So, this is the basics of polar representation. Now, we shall see some examples to understand how this can be better implemented. Now, let us say I have a complex number which is represented in a Cartesian form, namely in ordered pair. So, this is 2 comma 2, the ordered pair 2 comma 2 means that the x coordinate is 2 and the y coordinate is 2. And now, I have to convert this into a polar coordinate, and therefore I am just going to work out the mathematics behind it. We already recall that r is equal to root of x squared plus y squared. So, r is root of x squared plus y squared means that we know that x is 2 and y is 2, and hence you just substitute those values and you are getting that this is 2 squared is 4, another 2 squared is 4. So, 4 plus 4 is 8, therefore, root 8 is 2 root 2, and this is the length of the vector r. Whereas, the polar argument, this angle t is what we are going to find here, and for that we remember the formula, which is t is tan inverse of y by x plus k pi. So, I am going to just apply that there. First of all, let us find the principal argument alone, the principal argument which is excluding k pi, excluding k pi. So, the principal argument is tan inverse of y by x alone, which is tan inverse of 2 by 2, which is tan inverse of 1, and hence t is equal to pi by 4. So, the polar coordinate of 2 comma 2 is r comma t, which is 2 root 2 comma pi by 4. Now, you can see that 2 is also greater than 0, y is greater than 0, and x is also greater than 0, which means that k value is 0 here, because x is greater than 0 and y greater than or equal to 0, and we have the Cartesian coordinate 2 comma 2, both of which are greater than or equal greater than 0. Hence, k becomes 0, and hence we have only the principal part. So, tan inverse of y by x alone, we do not have plus k pi. So, this is how we solve for this. So, polar coordinate of 2 comma 2 is represented as r comma t, which is 2 root 2 comma pi by 4. So, this is a polar representation. Let us go to one more example. Convert the rectangular 1 comma 0 into polar coordinates. So, this is also represented in the form of a Cartesian coordinate, namely 1 comma 0. Now, keep in mind that y is 0 here. So, which means that you may need to pay attention here also. If y is 0, what do we do? So, we have one case here. Then, so given x comma y is equal to 1 comma 0, the polar radius is given by, as usual, the formula is r is equal to root of x squared plus y squared, which is root of 1 squared plus 0 squared, and hence that is 1. So, the length of the vector is 1, and whereas the argument or the angle with which it is going to work. So, polar argument of the point 1 comma 0 is given by tan inverse of y by x, but we do not consider, because here k is 0, since we have y to be 0 and x is greater than 0. So, tan inverse of 0 by 1 is tan inverse of 0, which is 0, hence angle is also 0. So, polar coordinate of 1 comma 0 is also 1 comma 0. Next, one more problem to do this, to understand this better. Let us convert a polar coordinate into a Cartesian coordinate. So, so far we had only seen Cartesian to polar. Now, we are going to see from polar to Cartesian. So, let us say I have been given a polar coordinate r comma t as 4 comma pi by 2. So, 4 represents the length of that vector, and pi by 2 is the angle. So, t, r and t have been given here. How do I convert it into a rectangular coordinate? We just have to reverse the process, that is all. So, r comma theta is 4 comma, so earlier we were using the notation t, it can also be theta. So, it does not matter, sometimes we use t, sometimes theta. So, r comma theta is 4 comma pi by 2. Here r is equal to 4 and theta is equal to pi by 2. So, how do I do that? So, we know that x is equal to r cos theta and y equal to r sin theta, that is all. So, merely representing the terms will give you the values. So, 4 into cos pi by 2. So, pi by 2 is the angle given here. So, 4 into cos pi by 2 is 0, and then y equal to r sin theta, which is 4 into sin pi by 2. We know that cos pi by 2 is 0, so that part is completely 0, whereas y you have sin pi by 2 is 1, and therefore 4 into 1, 4. So, the rectangular coordinate or the Cartesian coordinate becomes 4 comma pi by 2, which is converted to 0 comma 4 in terms of x and y. So, that is all for understanding about conversion of rectangular or Cartesian coordinates to polar coordinates and vice versa. We shall now see polar representation of a complex number. The polar representation of an arbitrary complex number z equal to x plus iy is represented as z is equal to r cos t plus I sin t, where r belongs to closed interval 0 comma infinity, infinity being on the open interval side, and t belongs to closed interval 0, open interval 2 pi. And these are the polar coordinates of the geometric image of Z. The polar argument t of the geometric image of Z is called the argument of Z, denoted by arg of Z or arg Z. The polar radius r of the geometric image of Z is equal to the modulus of Z. It is noted that the argument of Z is a multi-valued function. If t is an argument of Z, then arg Z is equal to the set of all t plus 2 k pi such that k belongs to Z are also the arguments of Z. This set is called the extended argument of the complex number Z. Corresponding to every non-zero number Z, there is exactly one argument in the interval closed interval t, open interval t plus 2 pi. Consider the function f from C, where C does not contain 0 to R, such that f of Z is equal to arg Z. If we restrict the codomain R to any other interval, then the function is called branch. The function from C set minus 0 to open interval minus pi, closed interval pi, such that f of Z is equal to argument of Z is called the principal branch. We shall see some examples to understand polar representation better. So, I am going to represent the polar representation of this number Z is equal to minus 1 plus I root 3. Now, we need to pay attention to what is the real part and what is the imaginary part. So, Z is x plus iy. So, x here is in the negative format and y here is in the irrational number. It's a real number of course, but it is positive whereas x is negative. So, as we can see, I have just merely represented it in the form of a Cartesian format first. Let us not look at the angles for now. Now, this is the x axis and this is the y axis as we have in a 2-dimensional scale. And so, minus 1 comma root 3 is merely, so if I were to represent root 3 on the y scale and minus 1 on the x scale, I have merely plotted the position of p, that is minus 1 comma root 3 here. So, this is merely a Cartesian representation, and now I am going to calculate the polar radius and the polar argument. So, polar radius as we know is r is equal to root of x squared plus y squared, which is root of, so minus 1 root 3. So, minus 1 squared plus root 3 squared, which is root 4, and that is equal to 2. Whereas, the polar argument is tan inverse of y by x. Now, as I said, we need to pay attention to the number here. So, there is a negative x axis, hence we represented this the polar argument as t tan inverse of y by x plus k pi, but here k is equal to 1 because x is negative. So, t is equal to tan inverse of root 3 minus 1 plus pi, which is equal to tan inverse of minus root 3 plus pi, which is equal to 2 pi by 3. Since we have added pi, it becomes 2 pi by 3. So, the polar representation of Z, which is in terms of x and y, is minus 1 plus I root 3. This is one more representation. This is not exactly a Cartesian representation, but another representation of a complex number. But we are only considering this as the Cartesian part of it. So, minus 1 comma root 3 can also be represented in terms of this vector r, which goes from 0 to this position. So, this r length is determined by the polar radius, which is equal to 2. So, this length should be 2 and the angle is 2 pi by 3, which is again 120 degrees. So, you can see that it is an obtuse angle and it is going from 0 to 120 here. Can you see that? So, this is a polar representation. So, the polar representation of Z equal to minus 1 plus I root 3 is 2 cos 2 pi by 3. So, cos theta plus I sin theta, that format. So, here cos t plus I sin t, if you are using the term t here. So, cos t is 2 pi by 3 and I sin t is 2 pi by 3. So, 2 cos 2 pi by 3 plus I sin 2 pi by 3. This is the polar representation of a complex number. Now, let us see another example, polar representation of one more number. Here note the x and the y, it is both negative. It is both negative. X is also minus 1 and y is also minus 1 here. So, minus 1 minus I. Now, if I were to represent it in merely Cartesian coordinates, so x axis, y axis, so -1 comma -1 means that the point will be somewhere here. So, p -1 comma -1. So, if I were to plot it in Cartesian format, this is what I would get. But let us check if the polar format is also coinciding with the Cartesian format, which it will of course, but let us now do the math behind it. So, polar radius of -1 comma -1 is again r equal to root of x squared plus y squared, which is root of -1 whole squared plus -1 squared, which is root 2. So, I need to draw something like this. So, from from 0 I draw root 2 from here to here. Again the angle has not yet been determined. So, actually I can draw r equal to root 2 anywhere like this. Since the angle has not been determined, we do not know where to draw root 2, but we just know that the length of the vector can be root 2. So, the angle part is important to determine where you have to draw the vector. So, polar argument of -1 comma -1 means that t is equal to tan inverse of -1 by -1 plus pi. Again, since my x is negative, I can go for plus k pi. So, plus k pi here, k is 1. If you can recall what we studied earlier, we know that it can take the value 0, 1 and 2, but since x is negative, it takes 1 value here. So, tan inverse of -1 by -1 plus pi, which is tan inverse of 1 plus pi, and we know that tan inverse of 1 is pi by 4. So, pi by 4 plus pi is 5 pi by 4. So, the polar representation is r cos t plus I sin t. So, r is root 2. So, cos 5 pi by 4 plus I sin 5 pi by 4. Now, 5 pi by 4, if I were to draw it, it looks like this. So, where should I draw my r equal to root 2? I must first identify an angle that makes an angle 5 pi by 4 here. So, from here I can draw my r equal to root 2, and therefore, this diagram represents my polar representation of the complex number. Now, let us see one more example. Let us completely remove the x part. I just have the y part here, and that is also negative. So, x here is 0, whereas y is -3, and so our usual technique, r equal to root of x square plus y square, which is root of 0 plus -3 square, which is 3 naturally. So, and t will become tan inverse of -3 by 0. If you remember in the previous section when we were discussing about k, we also said that whenever x is 0, it is either pi by 2 or 3 pi by 2. So, without even doing all these calculations, I can say that it is some value, but just to ascertain which of those two values, pi by 2 or 3 pi by 2, I need to do a bit of mathematics here. So, tan inverse of -3 by 0 I get, which is tan inverse of negative infinity, and that becomes 3 pi by 2. So, tan inverse of positive infinity is pi by 2, whereas negative infinity is 3 pi by 2. So, it is 3 pi by 2. And so, the polar representation, so r has already been calculated, therefore, the polar representation, the formula is r cos t plus I sin t. So, r is 3 here, and cos t is cos 3 pi by 2 plus I sin 3 pi by 2. Dear learners, in this session we learnt about complex numbers, their origin, and also some of their applications. We also learned about polar coordinates in the plane and the polar representation of complex numbers. Numerous examples associated with these concepts were also illustrated. I hope that they were useful for you to understand complex numbers and their various representations. Thank you.